Today we are going to be taking a look at this, the Micsig CP2100B current probe for an oscilloscope. Now this device allows you to measure current versus time on an oscilloscope, just like a traditional probe allows you to measure voltage versus time. You might be asking yourself, well, why do I need something like this when I can measure current on a multimeter such as the one I've got here? Whilst a multimeter is an extremely capable device allowing you to measure voltage and current, it really only gives you two-dimensional data in the sense of it's telling you what the current voltage is or what the current draw is at the time. A probe, such as a current probe on an oscilloscope, allows you to get a lot more detailed information because you're measuring that current versus time, and you have the ability to see things such as inrush current changes, the ability to see what the voltage versus current phase is for things like power factor, and you can even see what the switching frequency is on a switch mode power supply. Today, what we'll do is take a closer look at this probe. I'll walk you through some of its features and capabilities. We'll get it on the bench and show you it in a few different scenarios to give you an idea of the kind of things that you can use a current probe for. Just to be clear, Micsig have sent me this probe over for free to allow me to be able to make today's video, and I just want to say a massive thank you to them as well as Telonic Instruments in the UK to enable us to be able to do that. What we'll do first is get it on the overhead and take a look at what the probe is all about and what you get included in the kit. Then we'll get it on the bench and see how it actually works. So first of all, taking a closer look at the probe's hardware itself. The nice thing with all of these things from Micsig is they generally come in this plastic case that you can see. It's a nice carry case with a handle on the top, keeps everything nice and secure, and whether you're having it on the bench or out and about, it's just nice to know that it's all kept inside and it's nice and protected and it's not going to get damaged. Opening this up, we have two levers, one here and one here, and when you lift the lid, you will find inside that you will have this little certification leaflet, which just tells you about the testing info for the device itself. We have our instructions as well as specification sheets. We've got the spec on the back as well as the instructions on the front. And then inside, you will find the probe itself. As I've said, the model I've got here is the CP2100B. This is the higher specification version of the probe. If we look on the list on here, it shows us the full specs on the back. So this one supports DC to 2.5 megahertz frequency range, 140 nanoseconds rise time, and it supports a potential accuracy of 3% plus minus 50 milliamp on the 10 amp setting, and this one goes either up to 10 amp or 100 amp depending on what setting you set the device to, and then it has all of the other specifications listed down there. Now, like many of the other probes that you find out there, this one is powered and they supply a USB cable. There's a USB-A connector on one side and a USB-B on the other, and it will need to be powered either from a power supply, or if your scope has a USB output like most of the modern ones do, you can simply plug it in, and on all the Micsig scopes there's an output for it as well. You'll see the probe itself simply consists of the probe, the clamp, as well as the wiring. If we just take it out of the box and put that out the way. Now it's all out the box. You can see we've got the main probe itself, we've got the grey cable that heads off to the current sensing clamp, and then we've got the black cable, which is our cable that goes to the scope with a shrouded BNC. The clamp is a traditional style current clamp. You can simply open it up like that. You can see the internal area there where you have the metal that goes around all the way for the sensing, and then the actual sensor is buried down in this section of the clamp here. It has a nice spring action and can cope with cables up to 13 mil. Something to note on this clamp is it is directional, so you'll see printed on the top here, it shows an arrow of direction, so you need to make sure when you're clipping it onto your cable, you do have it for the correct direction of current travel. So again, you can simply clip it onto a cable like that for doing the current measurement. Looking on the probe itself, we have our 10 amp and 100 amp selection, which again selects what range we want to be looking at and the accuracy is going to behave in. We have our adjustment here, which is our reference adjustment, which we'll take a look at a little bit later, but you can basically adjust the reference on the probe as well as on the scope as well. And we have a 0 button. You will need to 0 the probe before it's used, and you should do that in free air. So what you would simply do is have it away from anything electrical before using it, hit the 0, allow it to calibrate itself, and then you're able to use it. All the rest of it you have is a USB-B, which is our connection to go to our scope via that supplied cable. And then you have a voltage pass-through over here for a USB-A that allows you to pass voltage on to another device if you wanted to daisy chain. Overall, that is the basics of the probe. There is nothing specifically difficult here with regards to using it. You would simply plug it into your scope, choose the range, 0, and then connect it up to our source that we want to measure. What we'll do next is get it onto the other bench and take a look at it in action. Today we're going to be setting the probe up on this, the STO1104E portable oscilloscope from Micsig. Now, overall, the setup is the same no matter what scope it is, but we're going to be showing you what it is on this one specifically. So the first thing we need to do is take our probe input and we're going to place it onto channel 1. You could put it on any channel you wanted to use it on. So for instance, if you wanted to use voltage on channel 1 and current on channel 2, that's absolutely fine. You just need to make sure you configure it as such, which we'll take a look at in a second. Next, we then have the probe itself. We've got the USB cable plugged into the bottom, and we're then going to take the USB-A and plug that into the side of the oscilloscope, and that is going to provide the power for the probe. And as you just saw then, you can see the lights have come on. We now need to configure the scope to tell it that we're using a current probe rather than voltage, and we need to do that on the selected channel. So for us, it's channel 1. On this scope, it's nice and easy. We simply go over to the channel 1 options and we change the probe type from voltage to current. And then we need to make sure that we have the setting here, which is the ×1 ×10, the input settings correct as well. On this probe, if you have it on 10 amp, you need it on ×10. And if you're going to use it on 100 amp, you would use it on ×100. So it's very easy to do, but you do need to make sure that you do get that right before using it. Now that we've got it set up, we've got the probe correctly aligned, what we can then do is do the calibration. Now, as I've said, you need to calibrate the probe in free air before using it on whatever device you want to be measuring. So what I'm going to do is simply place the probe here on the bench on its own, and we're then going to press the 0 button, and what that will do is take a 0 reading from the probe. It'll beep a few times and then it will be ready to use. So what we'll do now is hop over to the bench, get it on a switch mode power supply first of all, and show you something on that. So to demonstrate the first thing, which is a switch mode power supply, I have a slave plug socket here, which has a nicely longer looped live connector. This is simply to allow me to take the current clamp, clip it onto the wire nice and easily, and then I can test anything we plug into that rather than testing each individual device. The first thing we'll do though, before we do anything again, is 0 the unit, just to make sure that it is calibrated correctly and we know the readings we're going to get are what we would expect. So that's all done. We can clamp that onto there. We've got our scope set up as we did just now, and we're going to plug in this switch mode power supply. Now you can see up on the screen, we've got a waveform up here, and we can now see what is actually being drawn by the switch mode in general. If we just zoom it in a little bit, you can actually see the current on the switch mode as it's actually drawing. You can see we're getting basically 50 Hertz, which is UK mains frequency. And you can see we're getting a peak to peak of about 1.2 amp. And that is the current draw that we're currently getting from this switch mode power supply. Now, there is a lot more I could go into here with regards to power factor at this point, but we're not going to do that in this one. Dave at the EEEV blog does a great video actually on the same probe, and I don't really want to replicate the same thing, but he starts talking about the waveform and why you're seeing the spikes and stuff like that. But the basics are, as you can see there, we're measuring the current being drawn. Now, Dave did actually show this, but I'm going to show it as well because it's really, really interesting. And that is, you can sort of see what the switching frequency is of the switch mode power supply as well. To do this, you need to zoom right in on the waveform. So what we'll do is we'll zoom in, move along a little bit. We'll increase the voltage height slightly. And then we'll move it just so we can see it a bit easier. And what I'm going to do is stop the actual run a second, zoom in, and you can actually see this little waveform on the signal. So if I start run again, you can see the waveform is simply being shown. So there is this little waveform that is demonstrated there. What you can actually do with this, though, is use this to try and figure out what the switching frequency of the power supply is. So if we turn on our cursors, and what we can do is go to here on that one and put that cursor on that peak, and then put that cursor on that peak, and you can see that that's showing a frequency of 96 kilohertz. If we move that along, it pretty much keeps it at the same position. Yeah, a bit of a dip there, but again, pretty much the same there. Again, pretty much the same there. This isn't 100% accurate method of measuring this, but it does give you an indication of what you can do. So again, if we run it and zoom out a little bit and then move our position along, we could come along here further along the waveform and stop it. Again, zoom in further to make our life a little bit easier. And then again, you can then measure what that switching frequency is, and it's going to give you then an indication of what it is that that power supply is doing. We could do it there, but it's a bit easier if you actually stop it so you can do the adjustments. That way you can just make it a bit easier, but that is showing 96 kilohertz. So again, if we stop it there, you can see we're getting 84, 85 kilohertz on that one. So on switch modes, it just allows you to get in there and see some nice, easy information, not only the current draw, but you could even dive in a bit more and see, is the switch mode behaving as you would expect? Is there something odd happening with the output? And the probe allows you to be able to see that quite easily on the scope. What we'll do next now is hop over and take a look at an inductive load. Now, the reason I want to do an inductive load is because it will allow us to take a look at the current and voltage phase and actually see if they are together or if they're shifting. We'll take a look at it on the switch mode first, but we'll then take a look at it on the inductive load and demonstrate the effect of an inductive load with regard to that power factor and how it can drag the current at a phase from the voltage. So now we have our differential probe connected up to the scope as well on channel 2. It is looping through into the current probe for its power, and then that is getting its power from the oscilloscope over here. So the nice thing is you can actually daisy chain these up from a power point of view to supply each other, and we've got the differential probe connected up to the socket with the current sensor there as well. As you can see on the screen, we now have our two waveforms. We have our voltage at the top in blue and our current at the bottom. The nice thing is, if you see, they are both aligned. So if I just turn on the cursors a second, you can see if we look at the peaks of the waveforms, they are aligned with each other. So for instance, the peak of the voltage is aligned with the peak of the current. The lower point of the voltage is aligned with the lower point of the current, which means the voltage and current are in phase. You could say that the load that we have on here has a good power factor because they are basically aligned. However, if we move over to a different kind of load, something such as an inductive load, for instance, that will start to change how that curve looks. So what I will do is go and swap that over, and we'll come back and take a look at that. Okay, so we've got an inductive load connected up, and this is a small bench grinder. It's not a very large motor on this, but it is enough for me to be able to demonstrate the effect. So what we're going to do first of all is kick it on with the switch, and you will see it draw a high amount of current first of all, and then that fade down as it gets up to speed. So what we can then do is adjust the amount of voltage reference on the side. So we'll pick it there, and everything looks perfect. Now, the first thing you'll notice now with this load is that the voltage and current are no longer synchronized, or they are no longer in phase. So for instance, if we look at the peak here for the voltage, it is no longer the peak for the current. The current is actually lagging it slightly. If we then go to the bottom peak, so if I just drag ourselves back to the center, actually, quickest way to do that is that. You can then see that this side of it is off phase as well. So what's happened now is the current has started to actually lag the voltage, and that is as a result of that induction motor. And you can use these probes for seeing the effect of these and seeing what the power factor of the device is actually like as a result of this lagging effect. The last thing we're going to do quickly is just take a look at some inrush current measurements with the probe. Now, I've got it hooked up to a quad on the bench, we've got it on the battery, and what we're going to do is put it in single shot mode on the scope, or single capture, and then we'll plug the battery in, and that will allow us to have a look at what kind of current spikes we get when we actually connect the battery up, and just giving you an idea of the kind of numbers that you can see even on things like this. And we'll take a look at some goggles and stuff now as well from the FPV side of things. So what we'll do is we'll just unplug the quad, we'll set it to single mode, which is clears the display, and then we'll go in, and you can see instantly that massive inrush current that was visible on the input. Now, if we zoom in to take a look at this, so what we can do is zoom into the scale, and you can see the point that nothing came in. And you can see at that point, there was a peak or a max of 14 amp in total. So that is a huge amount of current for a second as we connect up. And then as we scale out or zoom along, you can actually see the spikes from the motor beeps as it fires up, as it's drawing that current. But the real interesting one is that one here, because that is the one that is the main initial inrush spike as soon as you power the device up. So it gives you an idea of the kind of numbers that can be involved, and that's why you get sparking on connectors like this, the XT60. If we take a look at a couple of other devices as well, I'll go and grab the goggles. So here we have the DJI digital FPV goggles. We have our LiPo, again with the current sensor all connected. So what we'll do again is simply plug in on our single set mode, and you can then see on the display that current spike that has been produced. You can see maximum of 3 amp. And if we wanted to get in closer and look at that, we could actually do that, zooming out, and just see that spike in a lot more detail on the display. So again, it's nice just to be able to see the kind of current levels that can be involved when you are plugging devices in. Not only can you use it for that though, if we go over to the live, we'll be able to see that we're currently drawing about 1 amp on these goggles at the moment. So we can see that the current draw is about 1 amp. If we scale it out, it doesn't really show us much when we come out. We just simply get the overall numbers. Again, nice and easy to be able to see what the devices are pulling. We could go on to some much lower power devices as well if we wanted to demonstrate it, but the reality is it gives you an idea of the kind of things that you can do with the current probe. Very handy for AC devices, whether you want to have a look at switch mode supplies, whether you want to have a look at things like power factor or what is going on, but also alternatively on the DC side of things as well. Very interesting to be able to see what the kinds of inrush current you're seeing when you plug the device in, and you have the ability then to design your circuit or adjust your circuit to try and alleviate that. Now that is pretty much everything I'm going to show you on this one today. I have to say these are very handy bits of kit, and if you're interested in getting yourself one, I will put a link to Micsig's website as well as Talonic Instruments in the UK where you can order yourself one of these. You don't realise how handy a tool like this is until you actually have access to one, and I found myself using it more and more all of the time, and it works extremely well even on the very low current devices that I use here on the bench for the Model RC type stuff that I do a lot of. But it also allows you to dig in a lot deeper into things that you're building, such as checking out that inrush current, looking for voltage and current spikes, and even look at what the power factor situation is. If you're someone that works on switch mode power supplies, it also gives you that interesting capability of having a look at what the switching frequency is. Does it appear to be looking right? And if you then combine it with something like this, which is the differential probe, you can get in there and get a lot more info than you would ordinarily be able to do. And Micsig have a really good range of accessories for oscilloscopes that work with not only their own ones, such as the portable one I've got here, but they will work with other oscilloscopes as well. The nice thing about pairing these devices up with the Micsig portable one is that you can take it out and about, but you can use it on the bench as well. And for me, it gives me the best of both worlds, especially not being tethered to a 3-pin plug. As I've mentioned, I'd like to thank Micsig for sending this one over to me, and if you're interested, please do check out the links. I hope you have found the info in this video useful. If you are interested in finding out more, if you want any other questions, please do put them in the comment section. I'll try and answer them as soon as I can. Anyway, that's it from me on this one. Stay safe. Please do hit the subscribe button if you're not subscribed here already, and hopefully I'll be making some more content on this in the near future.